Okay, now we're going to be talking about the total differential and its relation to state functions. So we just have this blanket statement here. We say that all state functions have total differentials. Okay, so let's say we take pressure, for example. Based on that statement, we should expect it to have a total differential, but we actually want to prove that. Or we want to make sure that we can actually say that instead of just going off of what your book says, or whatever I'm saying in this video. You want to make sure that you understand the material and that you can show that to yourself. Okay, so we have that the total differential for pressure, we're going to write dP is equal to the partial of P with respect to T at constant V dt plus the partial of P with respect to V at constant T dV. Okay, and we can write this because we have the general expression for the total differential is dz. So some function z, we're taking the total differential of it. If it has a total differential, we have dz plus some function that some function m that's a function of x and y dx plus another function n that's a function of x and y dy. Okay, but the functions m and n are defined themselves. So let's say m, we can define that as the partial of z with respect to x at constant y. And then the function n, we can define that as the partial of z with respect to y at constant x. Okay, so that's where we get our general expression from that we can then use to rewrite the differential form of pressure, dP. Okay, and the dP, the differential form, writing the total differential for pressure, is going to equal nR over V dt minus, sorry, voice crack. So minus nRT over V squared dV. So quick recap. What are we doing here? Okay, so we've got this function, we've got the state function P, and we're like, okay, well, number one, we want to see if we can write it in differential form, and then also we want to see if we can say, let's prove it's a state function by putting it in differential form. Okay, so we're going to say that from this condition, if you watched the last video, we said that we want to check our mixed second derivatives to see if there's a differential for this general function z. In this case, z is P. It's pressure in this case, instead of just saying z. And the way we're going to do that is we're going to see if the partial of m with respect to y at constant x is equal to the partial of n with respect to x at constant y. We have to check that. So down near the bottom left, we're going to write the partial of m with respect to y at constant x, and then we're going to get dt over dv, and then we're multiplying that by n times r over v. Okay, and what we end up getting when we take this derivative here, when we take the derivative dt dv, we're going to end up with negative nr over v squared. Then we repeat the same procedure for the partial of n with respect to x at constant y, and we get that minus nrt over v squared, and then there's a typo in the video. It should say that we've got dv dt. So writing dv dt instead, if you're copying this down, that we have the derivative of v with respect to t instead of the other way around with the last function we looked at where we had dt dv. So if we take dv dt, we get minus nr over v squared, and that's the exact same thing that we had for the partial of m with respect to y at constant x. Okay, so we can say that dP is a total differential and pressure is a function of state.